Okay, so we're going to try to implement pixel explanation algorithms, because I've been doing this thing for a while where we take a pre-trained classifier, backprop, or compute the the gradient of, so we start with a random image, compute the gradient of the image, the pixels with respect to a class output. And so using that technique, you can find images that look like random noise that activate very highly one of the class outputs for the pre-trained classifier. And so we're simply trying to see if it's possible to understand like what is happening. So like these images, these are all the same image. This is like an ablation study. And but this image, it activates very highly analog clock as a classification. So the classifier is somehow seeing an analog clock. And yeah, we're trying to figure, I mean, it's possible that this phenomenon perhaps is not even explainable. I mean, it's possible that, because like when you train, like this is MobileNet trained on ImageNet, it's conceivably possible that, you know, like the classifier, or I guess like if you, so the input space of MobileNet is like a hypercube in a very high dimensional space, and it's the interior of the hypercube. And so it's possible, like, you know, the MobileNet, when it sets up like its decision boundaries, for instance, for a class, you know, it's only ever trained on like natural images. So it's possible that like when it sets up those image boundaries, or the decision boundaries, that the decision boundaries like extend past the natural image manifold. And so like you're always going to have like basically incoherent images that activate classes like without any particular reason why. Like it could be the case that if you retrained the MobileNet, like it could be the case perhaps like this image no longer activates as analog clock. That'd actually be a pretty good experiment. I'm gonna write that down. Maybe I'll do that in the next, thing. To do, if retrain classifier do the same random images, activate the same classes. Also, like a version of this question would be if you do the same fake images, activate same outputs on, e.g., MobileNet and, you know, one of the other classifiers. Yeah, that's like, that's something I could do. But what we're trying to do, what we wanted to do in this video was use, I think, pixel saliency methods to see if, you know, I mean, like to the naked eye, these images do not look like analog clocks. But I suppose it's conceivable that if you highlight a certain subset of the pixels, then it might resemble an analog clock. So that's what we wanted to test, and so we're using like pixel saliency methods. Like the most basic pixel saliency method is this ablation method, where you just walk a gray square across the images, and that does produce like interesting results. Like in particular, like the three, so on the top row, like these three images are not classified as an analog clock, which seems to imply that there is something, I don't know, like in this image patch that is necessary for the classification. And so you could actually, you could do like the inverse, like if you've found a patch that if you ablate it, it changes the classification. You could do like the inverse, where like if you just keep that patch and you delete all of the other pixels, with that, I mean, like, I don't know the logic of that, because like if you only keep that patch and like it's still classified as a clock, it's like, okay, there's clearly something that looks like a clock in that patch. But if you only keep that patch and you delete the rest of the pixels, and when you delete the rest of the pixels, it results in not being classified as a clock. I don't know what the interpretation of that would. Well, it'd be yeah, like there's something in that patch that is necessary, but not sufficient to be classified as a clock. Okay, so anyway, but we wanted to talk about like guided backpropagation, which is one of the main saliency methods. And yeah, this is what it's supposed to look like. So we're hoping in our images that it finds some, subset of pixels that resemble a clock. And so this is a combination of guided backpropagation and this cam method. And we found an implementation of the cam method on the Keras website. So I think we're gonna walk through this implementation later, because we don't fully understand it. But we also need an implementation of guided backpropagation. Yeah, like this is what the cam method does, right? The cam method is saying, I'm not entirely sure what it's saying. It's saying like, yeah, it's saying like if you take like the last layer, the last convolutional layer, and like you weight, and then you sum them together. I think like you weight each feature map by its average activation on this input, and then you sum all those you just sum the feature maps together. And then I guess like you normalize. You end up with this, which can be overlaid on this. And so it's saying that, yeah, like there's something in this part of the image that the partial derivatives are like high. which means, yeah, so like if you increase the intensity of I think pixels in this region, it's saying like those would increase the class activation. It is kind of weird because like we're generating these images using the gradients, and then we're looking at the gradients to look for salient pixels. So it's not entirely clear that is like sensical. So let me nevertheless try to implement guided backpropagation, and there's not like a huge amount of explanation of what guided backpropagation is anywhere. I thought I had a paper on it, and yeah, like this is the whole explanation for guided backpropagation. So you say backpropagation generically is the partial derivative of I guess this is like by layer. Because I mean even that I don't think is strictly correct, because you're supposed to have the weights. Are not you supposed to be multiplying by the weights? But they're saying like you take into account, because like it's a ReLU. So if the ReLU, it only matters if the ReLU is greater than 0. Otherwise, the partial derivative is 0. I mean, it seems like the way you would implement that would be like because you actually need all of the activations. As outputs. You need to access like every single activation, because you're then computing the gradients or maybe just a backwards pass would work. So I don't know, like if you call, TensorFlow tape gradients on a, like of like a model's output with respect to an input, I think that's just going to give you the partial derivatives of the weights. I mean, it has to compute the partial derivatives of the activations, but I don't think it gives you that. TensorFlow gradients. The Y's, I know, but like, because like in the, let's see, in the gradcam implementation from the Keras website, yeah, they explicitly output the output from the layer. And last conv layer output. Yeah, and then they're saying like last conv layer output with respect to the class channel. I guess I don't entirely see how I mean, isn't that just standard backpropagation? Because F is a layer activation, and RL is the layer's partial derivatives. Because like we're backpropping all the way to the pixels, so I guess like I don't see how this is different from a standard backwards pass back through a ReLU non-linearity. Different ways, different methods of propagating back through a ReLU non-linearity. Right? I mean, like all the negative values go to 0. And so they're saying on the back pass of backprop, so if on the forward passive it was 0, it stays 0, and -2, 6, -1, -1, 3. Okay. So it's saying like, Okay, so it's also saying if the gradient, if the partial derivative is negative, you zero it out. Yeah. So yeah, like, I mean, these are all zeros, and then all the yellows are zeros. So the only thing, yeah. So yeah, so you'd have to implement in TensorFlow when you're computing the gradient, you want to zero out negative gradients. Which is well above my pay grade. But maybe Google knows how to do it. Zero negative gradients. I mean, you're basically ReLUing the backwards pass as well. Okay, what about like custom gradient? Custom gradient. To define a function with a custom gradient. Find gradient control over the gradients. Find a more efficient or numerically stable gradient. F custom gradient. Yeah, but I have like a whole model. Okay, yeah, I'm using Keras, so I'm thinking I might have to, maybe Keras has something. Keras custom gradient. Oh, can I can define the model. I mean, the thing is like every layer is an operation, and so like every layer is going to have a unique, is going to have a custom gradient. Guided backpropagation. TensorFlow. Spell it correctly. Okay, perfect. There's like 2 clicks. register gradient. Yeah, but this is like TensorFlow 1.0 or something. Is that okay? I don't know. Huh. Is this... Okay, you have to use like a register gradient. Now you have to override the TF implementation of ReLU. Holy. Okay. Yeah, I mean, this is like... Wow, so, what if I just use PyTorch? I mean... or JAX. Guided backprop. Although, do they have like pre-trained, like does MobileNet exist in PyTorch? I mean... Colored vanilla backprop. I mean, the thing is like when we're creating the images, like this is literally what we're iteratively adding to the image. And I think it's like these, the gradients go to 0. Because, right, I mean, like once the class is maximally activated, like the gradients go to 0. So that's why I'm thinking this entire method might not even work. Like, I might just have to do ablations. Guided backpropagation. Guided backprop saliency. Negative saliency. Gradient weighted class activation map. Heat map. Score weighted. Well. Yeah, what if I just did that? because I think that's element-wise multiplication. Huh. Okay. Yeah, we're gonna hit the what do you call it? Yep.